Hi, this is Stu Schwartz from MasterMathMentor.com. This is Super Free Response Practice AB question number 5. Super free response questions are similar to the typical free response questions in past AP exams. But instead of having the usual 3 or 4 subparts, these will have a great many more. It allows us to use the problem setup as a source of many inquiries that can be taken and allows us to do an in-depth study of the situation. Because of that, many calculus concepts are tested and some reiterated. Doing these will take more than the usual 15 minutes, but by tackling all subparts, you will know what topics you need to emphasize as you prepare for the AP exam. It is recommended that you go to the MasterMathMentor website and download the PDF with the actual problem and subparts. If you don't have a printer available, use a piece of paper for parts A, B, C, etc. This video will just show you the solutions, although you can fast forward at times to bypass the solutions and just show the problems. Question number 5 is all about differential equations. Differential equations are equations in the form of dy dx is equal to some expression. There are 2 types of differential equations that we study. First, separable. Separable differential equations are equations that can be put in the form of f of y dy is equal to g of x dx. This allows integration from of both sides, and we can then solve the equation, getting what is called a general solution. From there, we can find a particular solution with one given point. And once we have the solution to the differential equation in the form of y equals f of x, we can find the value of f of any value of k. A differential equation that is non-separable cannot be put in the form of f of y dy equals g of x dx. And if we have a non-separable differential equation, there are limits to what we can do. We would need to take a full course in differential equations in order to work with them. However, there are certain pieces of information we can get. First is a slope field. We can look at the slopes, which are generally little lines to represent the slope of the equation solution at any particular point. We can also draw tangent lines to the curve at a point because we know its slope. We could also use the first and second derivative test to determine information about the solution to the differential equation, even though we can't necessarily find it. Rather than just give differential equations, this super free response practice AB question number 5 gets into a real-life application using a topic that we can all relate to, a virus and the effect of a vaccine on it. In this problem, we will examine 2 situations, one that can be defined as a separable differential equation and one non-separable. And we will try to get information to see how vaccinating people will affect the number of infections. 5 reads, an island country is experiencing a virus. It has developed a vaccine that is expected to counteract the virus. Let X represent the number of people vaccinated, measured in tens of thousands, and Y represent the number of new infections, also measured in tens of thousands. Based on clinical trials, the relationship between X and Y is expected to be the differential equation dy dx equals 10y minus 15x. Question A reads, on the axes provided, sketch a slope field for the differential equation at the 12 grid points. And we see x running from 0 to 0.2 and y running from 0 to 0.3, creating 12 grid points. I set this up with a spreadsheet, letting x run horizontally, 0, 0.1, and 0.2, and y running vertically, starting at the bottom, 0, 0.1, 0.2, 0.3. And calculating 10y minus 15x, we see those values, and we then place them on the slope field. 3 points for this problem. 1 point for all the slopes along x is equal to 0. 1 point for all the slopes along x is equal to 0.1. And 1 point for all the slopes along x is equal to 0.2. B reads, find the equation of the line tangent to the curve describing the relationship between infections and vaccinations when 1,000 people are vaccinated and 2,000 people have been infected. And we want to graph it on the slope field. Remember that x represents the number of people vaccinated, measured in tens of thousands, and y represents the number of people who have been newly infected, measured in tens of thousands. So based on the scale, 1,000 vaccinations and 2,000 infections corresponds to the point 0.1, 0.2. So dy dx is equal to 10y minus 15x, and at that point we get 10 times 0.2 minus 15 times 0.1, which is 2 minus 1.5, which is 0.5. And that's the slope of our line. So our equation is y minus 0.2 is equal to 0.5 quantity x minus 0.1, or y is equal to 0.5x plus 0.15. It's easy to graph this line. We know from our slope field work that the slope at 0.1, 0.2 is 0.5. And since we have our equation y equals 0.5x plus 0.15, the y-intercept is 0.15. So it's easy to create the blue line, which represents the tangent line. 3 points for this problem, 1 point for finding the slope, 1 point for finding the line, and then 1 point for graphing the line. Question C reads, find the second derivative of y with respect to x in terms of x and y. We know that dy dx equals 10y minus 15x, so the second derivative of y with respect to x is 10 dy dx minus 15. Replacing dy dx with 10y minus 15x, we get 10 times 10y minus 15x minus 15, and that gives us 100y minus 150x minus 15. Only 1 point is allocated here, getting the correct answer. Question D reads, suppose at a given time there were 3,000 people vaccinated and 4,000 new infections. Use dy dx and the second derivative of y with respect to x to describe the growth of the virus. 3,000 vaccinated and 4,000 infections translates to x is equal to 0.3 and y equals 0.4. So dy dx equals 10y minus 15x, or 10 times 0.4 minus 15 times 0.3, which is 4 minus 4.5, and that is negative 0.5, which is a negative number. The second derivative is 100y minus 150x minus 15, and plugging in the 0.3, 0.4, we get 100 times 0.4 minus 150 times 0.3 minus 15, and that is negative 20, which is also negative. So dy dx being negative means that the new cases are decreasing. The second derivative, less than 0, means that the rate that the new cases are decreasing is increasing. That seems to be incorrect, but it works similar to acceleration. When a velocity is negative and acceleration is negative, that means that the particle is speeding up. That's what's happening here, that the rate of decrease is increasing. 3 points for this problem, 1 point for setting the point, 0.3, 0.4. 1 point for dy dx at 0.3, 0.4 and its interpretation, and 1 point for the second derivative at the 0.3, 0.4 and its interpretation. E reads, suppose at a given time there were 4,000 people vaccinated and 6,000 current infections. Does this mean that the number of infections is at a relative maximum? Justify your answer. 4,000 vaccinated and 6,000 infections translates to x equals 0.4 and y equals 0.6. dy dx equals 10y minus 15x, and that is 10 times 0.6 minus 15 times 0.4, and that's equal to 0. So there could be relative extra at that value. There are several ways to check it out, but we are going to use the second derivative test and take a look at the second derivative at that point. Second derivative we know is 100y minus 150x minus 15, and plugging in our values of x equals 0.4 and y is equal to 0.6, we get the second derivative is 100 times 0.6 minus 150 times 0.4 minus 15, and that is negative 15, which is less than 0. So since the first derivative is 0 and the second derivative is negative, there is a relative maximum at the point 0.4, 0.6. 1 point for establishing the point of interest is 0.4, 0.6. 1 point for taking dy dx at that point and interpreting it, and then 1 point for the second derivative test. Question F reads, on the graph provided, shade in the area where dy dx is greater than 0 and the second derivative of y with respect to x is less than 0. dy dx greater than 0 means that 10y minus 15x is greater than 0 and y is greater than 3x over 2. The second derivative of y with respect to x is less than 0 means that 100y minus 150x minus 15 is less than 0, meaning that y is less than 3 quantity 10x plus 1 all over 20. Both are easily graphed. Y greater than 3x plus 2 is above the line y equals 3x plus 2, which goes through the origin and the point 0.2, 0.3. Y less than 3 quantity 10x plus 1 all over 20 is everything below that line. And at x is equal to 0, the value is 0.15, and at x is equal to 0.1, the value is 0.3. So it's everything above the blue line and everything below the red line, giving this green strip. 3 points for this problem, 1 point for the equation where dy dx is greater than 0, 1 point for the equation the second derivative of y is less than 0, and 1 point for the shading. G reads, explain the significance of the shaded region in part F within the context of the problem. Since dy dx is positive, then the shaded region represents the values of vaccinations and infections when the virus is spreading. But since the second derivative is negative, it means that the spread is not as quick. So the shaded region represents those values of vaccinations and infections when the virus is spreading, but not as quickly as it was before. 2 points for this question. It must be stated that the virus is spreading, and then 1 point for not spreading as quickly. H reads, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation, and then graph it on the accompanying slope field. This question is not a straightforward one. However, it has occurred on the AP exam before, most notably on the 2015 exam, for which this problem is based. We start with saying that dy dx is the slope of the line, and that we know it is equal to 10y minus 15x. So we then use that m is equal to 10 times y, which is mx plus b, minus 15x. Multiplying out, we get m equals 10mx plus 10b minus 15x. This is a relationship, but it's not quite clear what we're supposed to do with it. We write 10mx minus 15x is equal to m minus 10b. And x, therefore, times the quantity 10m minus 15 has to equal m minus 10b. Now think about this relationship. It is true for any value of x. And if it's true for any value of x, then the only thing that can happen is that the 10m minus 15 has to equal 0, and the m minus 10b has to equal 0 as well. So if 10m minus 15 is equal to 0, that makes m equal to 3/2. And if m minus 10b has to equal 0, that gives 3/2 minus 10b is equal to 0, and therefore b is equal to 3/20. So we graph the line y is equal to 3/2 x plus 3/20. 3/20 is equal to 0.15, and that would be the y-intercept. And we just simply need a line with slope 3/2 from there. And we can see that the line is graphed in blue. 4 points for this problem. 1 point for substituting dy dx for m. 1 point for setting both sides equal to 0. 1 point for coming up with the values of m and b, and 1 point for the graph. If a student had trouble coming up with m and b, but still correctly drew the graph, they could receive the point for the graph. Question I reads, explain the significance of the line in the context of the problem. The presence of the slope field helps students to understand the significance of the line. It represents the values of vaccinations and infections when the virus is spreading linearly. If any points are above it, the infections will spread exponentially. Below it, and the infections will eventually stop. Just 1 point for this problem for saying that is when the virus is spreading linearly. Before the vaccines became available in late 2020, the spread of COVID-19 was exponential. As more and more people get vaccinated, the spread is getting close to linear. And once there is more vaccine in people's arms, hopefully the growth will be below the line and eventually will stop. Of course, this problem is only based on infections as a function of vaccinations. But in the real world, there are many other factors, such as masks, testing, social distance, and countless others that still might not be discovered. Question J reads, suppose that the country can vaccinate 1,000 people a day. At what rate will the infections change if there are 5,000 people vaccinated and 20,000 people infected? We now add in the concept of time, making this a related rates problem. First, we need to get our numbers according to the problem scale. 5,000 people vaccinated, 20,000 infections translates to x is equal to 0.5 and y equal to 2. 1,000 new vaccinations a day refers to dx dt is equal to 0.1. So dy dx we know is 10y minus 15x, and that is 10 times 2 minus 15 times 0.5, giving 20 minus 7.5, and that becomes 12.5. So dy dt equals dy dx times dx dt, and that will equal 12.5 new infections per vaccine dose times dx dt, which is 0.1 vaccine dose per day, and the vaccine doses cancel out and we are left with 0.125 new infections per day. But again, we have to then translate this back to the real life scale by multiplying by 10,000, and this refers to 1,250 new infections per day. This problem illustrates the importance of scale. When we're talking about huge numbers of infections and huge numbers of vaccinated people, it is impossible to use the real numbers, and we usually then divide by some constant. In this case, it was 10,000. So when we give the problem in terms of real numbers, we have to change it to scale. And that's why there's so many points for that. 1.4 changing x to 0.5, y to 2. 1.4 dx dt is equal to 0.1. 1.4 dy dx times dx dt is equal to dy dt. And then 1 point for the final answer. The country has another vaccine with different technology, which they believe will be more effective than the one previously investigated. As before, let x represent the number of people vaccinated, measured in tens of thousands, and y represent the number of new infections, also measured in tens of thousands. Based on clinical trials, the relationship between x and y is expected to be the differential equation dy dx is equal to 3x squared minus 6x plus 1 all over e to the y. K reads, shown are the slope fields for the expected virus growth based on the older vaccine and the newer vaccine. Explain briefly why there is more confidence in the ultimate effectiveness of the newer vaccine. The slope fields clearly show that the older vaccine has scenarios where the infections continue to grow. But in all cases in the newer vaccine, the infections will die out. Just 1 point for the correct answer. Question L reads, at the time the vaccine is introduced, there are 10,000 people infected. If F is the particular solution to the differential equation based on that information, write an equation to the tangent line to F, passing through that point. 10,000 people infected with no vaccines translates to the point 0,1. So dy dx at the point 0,1 is 3x squared minus 6x plus 1 over e to the y, which turns out to be 1 over e. So the tangent line is y minus 1 is equal to 1 over e times x, or y is equal to 1 plus x over e. 2 points for this problem, 1 point for the initial point, x equals 0, y equals 1, and 1 point for dy dx, and the answer. M reads, use your answer in L to predict how many people will be infected when 10,000 people are vaccinated. Does this give good evidence that the vaccine is effective? Explain. So 10,000 people vaccinated translates to x is equal to 1. So our tangent line equation, y equals 1 plus x over e, becomes y equals 1 plus 1 over e, which is 1.368, meaning about 13,678 people will now be infected, and those numbers are going up. It does not appear that the vaccine is infected based upon the tangent line. 2 points for this problem, 1 point for the prediction, 1 point for the explanation. N reads, use the information in part L to solve the differential equation. To solve the differential equation, we separate the variables and get e to the y dy is equal to quantity 3x squared minus 6x plus 1 dx. We can now integrate both sides, and we get e to the y equals x cubed minus 3x squared plus x plus c. Part L had the fact that when there were no people vaccinated, there were 10,000 people with the virus, and that was translated to the point 0, 1. So we get E is equal to 0 plus C, meaning that C is equal to E, and e to the y is equal to x cubed minus 3x squared plus x plus e, or y is equal to the natural log of x cubed minus 3x squared plus x plus e. 3 points for the solution of the DEQ, 1 point for the separation and then integration, 1 point for finding C, and then 1 point for the ultimate solution. Part O reads, use your answer in N to predict how many people will be infected when 10,000 people are vaccinated. Does this give good evidence that the vaccine is effective? And explain. 10,000 people vaccinated translates to x is equal to 1 by our model. So y is equal to the natural log of 1 minus 3 plus 1 plus e, which is the natural log of e minus 1, and using our calculator we get 0.541. So there are about 5,413 new infections, and the numbers certainly have decreased from where they began. So there seems to be some evidence that the vaccine is effective. More data would have to be examined. 2 points for this problem, 1 point for the prediction, and then 1 point for the explanation. Part P reads, scientists predict that fewer than 2,000 vaccines need to be given for the number of infections to reach its peak. Explain why this is true. To find relative extra, we set dy dx equal to 0, which means that the numerator 3x squared minus 6x plus 1 is equal to 0. By the quadratic formula, x will equal 6 plus or minus the square root of 36 minus 12 all over 6. And that gets 0.18 or 1.82. Concentrating on the first one, dy dx will switch from positive to negative at x is equal to 0.18, meaning that there is a relative maximum there. So, doing the translation, that means that fewer than 2,000 vaccines are needed to maximize our infections. 2 points for this problem, 1 point for finding the critical values for dy dx is equal to 0, and 1 point for the explanation why the one that we are interested in is a maximum. Part Q reads, based on your answer from Part N, write but do not solve an equation using only the variable v, which is the number of vaccinations that must be given for the number of new infections to be 0. We set our predictor equation y equals natural log of v cubed minus 3v squared plus v plus e, and we set that equal to 0. We need to get rid of the y, and we can therefore write e to the 0 is equal to v cubed minus 3v squared plus v plus e, and e to the 0 is equal to 1. So our equation is v cubed minus 3v squared plus v plus e minus 1 is equal to 0. 2 points for this problem, 1 point for setting our y equal to 0, and then 1 point for the final equation. Part R reads, based on the answer from Part N, scientists predict that between 10,000 and 20,000 vaccinations must be given for the number of new infections to disappear. Explain mathematically why this is true. For our model, 10,000 vaccinations corresponds to v equals 1, and 20,000 vaccinations corresponds to v equals 2. When v equals 1, the natural log of v cubed minus 3v squared plus v plus e equals the natural log of e minus 1, which is a positive number. But when v is equal to 2, the natural log of v cubed minus 3v squared plus v plus e is the natural log of e minus 2, which is a negative number. And because the natural log of v cubed minus 3v squared plus v plus e minus 1 is a continuous curve, then the intermediate value theorem states that there must be some value between v equals 1 and v equals 2, such that the natural log of v cubed minus 3v squared plus v plus e is equal to 0. For grading, 1 point for realizing that f of 10,000 is a positive number, f of 20,000 is a negative number, and 1 point for invoking the intermediate value theorem. S reads, a slope field for the DEQ is given. Sketch your tangent line from part L and your solution equation from part N. We see the increasing line in red and the solution in blue. And we don't have to have the exact graph of the solution equation. It just needs to follow the slopes. 2 points for this problem, 1 point for graphing the tangent line, 1 point for graphing the solution curve. There's a total of 46 points for this problem. There is no exact formula for what number of points will constitute a 5, 4, 3, 2, or 1 on the AP exam. However, these percentages are what have been used in the past based upon exams released by the College Board. While you can extrapolate for just this question, realize that this question only tests a limited number of AP topics. So it is recommended that you do a number of the super free response questions in this series. Then combine your results, total your points, and then use these percentages to get a feel for how you will do in the AP exam. And more importantly, what concepts you need to strengthen in order to improve your score.